So first of all, I would like to express my heartfelt gratitude to Annie Davina for kindly inviting me for providing this wonderful opportunity. So greetings to all respected chairpersons, distinguished guests and fellow researchers. I am Vishal Kumar, a research scholar from the Department of Statistics, Central University of Haryana, India. It is great honor for me to present my work at the 7th edition of Advanced Chemistry World Congress 2026. Today I will be discussing my research title Uncertainty Based Efficient Neutrosophic Imputation Methods for Population Mean. So, in modern data analysis, especially in interdisciplinary field like chemistry, we often encounter missing and uncertain data which can significantly affect the accuracy of statistical inference. To address this challenge, my research focuses on developing efficient neutroscopic imputation techniques that explicitly account for uncertainty and indeterminacy. So, in this presentation, I will firstly briefly introduce the basic concept and notations followed by the existing neutroscopic imputation methods. Then I will present my proposed enhanced methods along with their analytical properties, simulation results and real data applications. Finally, I will discussing the key findings and conclusion of the study. So let me begin with a brief introduction. So the introduction are divided into two parts. One is missing data, another one is Neutrosophy. So the problem of missing data is perennial and require immediate intervention so that the unwiseness and efficiency properties of an estimator are not vitiated. So the most appropriate and popular solution to the missing data is employing imputation of missing data. So the topic of missing data has been dealt by many authors and various imputation methods were adopted for imputing the missing data. And the availability of suitable auxiliary information plays a crucial role for developing the efficient imputation methods. Rubin 1976 in his notable work introduced three cardinal notations such as missing at random, observed at random and parametric distribution. So Hetijan and Vasu 1996 had discriminated the sense of missing at random and missing completely at random. Now missing completely at random is the combination of observed at random and missing at random, and various authors consider the missing completely at random outlook to impute the missing data. Lee et al 1994, Singh and Horn 2000, Singh and Dio 2003, Ahmad et al 2006, Singh 2009, Dina and Perry 2010, and Bhushan and Pandey 2016-18, and Singh et al 2020, and Singh and Usman 2021, and Bhushan et al 2022, and Bhushan and Kumar 2023 and 24. And most recent, Kumar et al 2024 proposed various prominent imputation schemes and corresponding estimator in sequence of handling issue of missing data. We now come to neutrosophic statistics. So neutrosophic statistics is considered as the quantity computed with some level of indeterminacy from the sample value. So it is a random variable having a neutrosophic probability distribution. So the long-term behavior of the values of neutrosophic statistic is described when the statistic is computed for many different values for the same size. So neutrosophic statistics is extension of classical statistics. The classical statistics with deal with precise formed by Cripps numbers, while the neutroscopic statistic handle with some degree of indeterminacy. So neutroscopic statistic is useful in chemistry for handling missing uncertain data simultaneously, like in water quality analysis. parameters like dissolved oxygen may be missing, while heavy metal measurement may be uncertain due to instrument errors. So the each observation is represented as a triplet such that truth, false, and indeterminacy. And in pharmaceutical chemistry, drug concentration data with missing readings and degradation uncertainty can be modeled more realistically. And reaction kinetics, uncertain parameters like rate, constants, and incomplete temperature data can be incorporated effectively. So this approach provides a robust and reliable result compared to the classical statistics methods. It improve it improves interpretation of experimental outcomes by considering both incompleteness and indeterminacy. So the best of our knowledge, there is no imputation method and the resulting estimator for estimating the population parameter in the presence of missingness associated with uncertain data. Therefore, we set up the following objectives. First one is to adapt some prominent fundamental neutrosophic imputation methods and corresponding neutrosophic estimator along with their properties. And second one is to propose enhanced neutrosophic imputation methods and corresponding efficient neutrosophic estimator with their properties, and to evaluate performance of the adapted and proposed neutrosophic imputation methods empirically utilizing indeterminate, hypothetical, and real data set. Now we are discuss the notations. So we are consider the random sample size of n, neutrosophic lower and neutrosophic upper is drawn from finite population, t is equals to t1 t2 up to tn, and small rn with the number of neutrosophic responding units from the extracted nn units, and capital Rn and capital Rn with the set of neutrosophic responding and non-responding unit respectively. So the value of y and I is obtained for each I belonging to responding unit. However, the I belonging to non-responding unit values are the missing and must be imputed fulfill the sampling data set. So the imputation of performed utilizing additional neutrosophic auxiliary information xni, the value of xni for ith unit available for the positive for all I belonging to Sn, ensuring that the data xsn is equals to xin are available. So the let y bar n belonging to y bar lower and y bar upper and same as x bar n be the population means corresponding the sample means, and sample means are y bar n belonging to y bar lower and y bar upper and same as the x bar n of the neutrosophic variable of the interest yn and the neutrosophic auxiliary variable xn respectively, and cyn belonging to cyl and cy upper and cy lower, same as the cxn, cy lower and cy upper with the neutrosophic coefficient of variation of the neutrosophic variable yn and xn respectively, and the neutrosophic correlation coefficient between the neutrosophic variable yn and xn is rho xyn. And to find out the y's of neutrosophic y's and neutrosophic MSC of the resulting neutrosophic estimators, we consider the neutrosophic error term. So these are the terms which are utilizing throughout the study. So now we are going to discuss neutrosophic adapted estimators. So the following Lee et al. 1994. The mean neutrosophic mean imputation structures are defined below, and the corresponding resultant estimator is given in equation 1. So in presence of additional neutrosophic auxiliary data, The neutrosopic imputation methods are divided into three methods described below. First one is when the neutrosopic population mean is available and the sampling neutrosopic mean is considered. And second one is when the neutrosopic population mean is available and the neutrosopic sampling mean for responding unit is considered. And when population neutrosopic population mean is not available and the neutrosopic sampling mean and neutrosopic sampling mean for responding unit are considered. Now the neutrosopic ratio imputation method, following Singh and Horn, the neutrosopic ratio imputation structures are given in method first, second and third, and the corresponding resultant neutrosopic ratio estimator are given in equation 2, 3 and third. And now neutrosopic regression imputation methods. So the following Dyna and Perry 2010, the neutrosopic regression imputation structures are given in method first, second and third, and the corresponding estimator are given in equation 5, 6 and 7, where beta I are the neutrosopic regression coefficient of yn on xn. Now neutrosopic power ratio methods. So the following Singh NDO 2003, we adapt the neutrosopic power ratio imputation structures are given in method first, second and third, and the corresponding neutrosopic estimators are given in equation 8, 9 and 10, where theta j are optimizing scalars. Now neutrosopic logarithmic imputation methods. So the following Wusan et al 2023a, the neutrosopic logarithmic imputation structures are given in method first, second and third, and the corresponding neutrosopic logarithmic estimator under the method first estimators are given in equation 11, 12 and 13, where the phi j are appropriate scalar to make MSC minimum. It is noteworthy that the minimum MSC of resulting neutrosophic power ratio estimators and neutrosopic logarithmic estimator is similar to the minimum MSC of the resulting neutrosopic regression estimator under the method first and third. Now we are discussing the most important part of the presentation, which are proposed neutrosopic imputation methods. So the proposed enhanced neutrosopic imputation structures are given in method first and second and third. So the corresponding proposed efficient neutrosopic estimator are given in equation 14, 15 and 16, where alpha j, gamma j and phi j are optimizing scalar. Also g and theta n are constant. Take the real values to design different enhanced neutrosopic imputation methods and corresponding resultant estimator. And the minimum MSC of proposed estimator are given in equation 17, and these constant values a b c d e are given in this slide, which are utilizing throughout the study. And now we are going to analytical study. So it is essential as it provides a systematic framework for evaluating the efficiency and robustness of the proposed imputation methods and resulting estimators. So through the analytical study, researcher evaluate the measures such as Bayes MSC and PRE, percent relative efficiency, to the systematically compare the efficiency of the proposed and adapted neutrosopic imputation methods in their resulting estimators. So this throughout analytical study helps in measuring the enhancement and robustness provided by the neutrosopic imputation methods while dealing with missing data. In addition, analytical study makes it possible to the situation which in which the neutrosopic imputation are most beneficial. So providing further understanding of its real life use, the eventually advances the statistical procedure in survey sampling. Thus we thus with these benefits we conduct an analytical study by comparing the minimum MSC of the proposed estimator adapted resulting under first under method first to third. Now, these are the analytical study where the proposed estimator is compared with the adapted estimators. And now we are going to discuss the simulation study. So it is important for verifying the theoretical result. Following Singh and Horn 1998, the following models are used to generate the Neutrosophic data. So the model are given in equation 18, which are follows. The xn and yn are independent neutrosopic variable and follow different neutrosopic distribution. So the simulation procedure is described below. So first of all, we generate a symmetric population for neutrosopic normal distribution of size n and size n 1000 and 1000, and utilizing with these values we generate the systematic population and select the sample size of 300 300 from the neutrosopic normal population generated in above step. Assume that responding units 280 280 units provided the responses from the selected sample nn, and drop nn minus rn unit from the selected sample nn, and compute the neutrosopic minimum MSC, mean squared error, and the percent relative efficiency of the neutrosopic estimator of the samples and responding units selected in previous step by considering 20,000 replications using the respected formula given in equation 19. So the simulated MSC is presented in table 1 and simulated percent relative efficiency presented in table 2 neutrosopic normal population. So the interpretation, now we are discussing the interpretation of simulation findings. So we can see that in table 1 MSC belonging to MSC lower and MSC upper of the neutrosopic estimator using neutrosopic normal population. So in method first we can see that the proposed estimator has minimum MSC, the adapted ones like the neutrosopic ratio estimator, neutrosopic regression estimator, and neutrosopic power ratio estimator, and neutrosopic logarithmic estimator. So we can see that similar pattern in the method second and third when we increase the correlation, and MSC, the proposed estimator has performed better than the adapted ones. Same as we can see that in table 2, which are for PRE, neutrosopic PRE. In method first, the proposed estimator has the highest PRE, the compare with the adapted ones like neutrosopic regression ratio estimator and neutrosopic regression estimator, neutrosopic power ratio estimator, and neutrosopic logarithmic estimator. So we can see that in whole table the same pattern follow the results. So now we are discuss the real data analysis. So to extend the simulation study, the proposed methods are illustrated through a real data related to daily stock price of NVDA Corporation. So the required descriptive statistics are given in table 3. So in this data, the neutrosopic survey variable by n is the varying price of stock on each day from 19 May to 2023 to May 19 2024, while the neutrosopic auxiliary variable xn is the varying price of the stock on each day from 19 May to 2022 to 19 May 2023. So the interpretation of real data results, the finding of real data are displayed in table 4 by Neutrosophic mean square error lower and mean square error upper, and relative efficiency lower and upper. The real data findings show that the mean square error of the proposed Neutrosophic estimator is the smallest compared to the MSC of the Neutrosophic sample mean, and Neutrosophic ratio estimator, Neutrosophic regression estimator, Neutrosophic power ratio estimator, and Neutrosophic logarithmic estimator. Also, PRE of the proposed estimator is the largest compared to the PRE of the adapted Neutrosophic estimator. Moreover, the performance of the proposed and adapted Neutrosophic imputation methods is superior under the method second among three considered methods. Now we can see that the MSC, so the proposed estimator has minimum MSC of the adapted ones like Neutrosophic regression estimator, Neutrosophic ratio estimator, Neutrosophic regression estimator, Neutrosophic power ratio estimator, and Neutrosophic logarithmic estimator. And we can see that for PRE, the proposed estimator has the highest largest PRE, highest PRE compared with the adapted ones like Neutrosophic ratio estimator and Neutrosophic regression estimator, Neutrosophic power ratio estimator, and Neutrosophic logarithmic estimator. So similar pattern we can see that in method second and third. Now we are going to conclusion. So in this article we introduce Neutrosophic imputation method and corresponding resultant Neutrosophic estimators of the population mean with their properties under simple random sampling. So the characteristics like bias and MSC of the proposed resultant Neutrosophic estimator are obtained to the first order approximation, and the proposed enhanced Neutrosophic imputation methods consistently provide more accurate and reliable estimates over the adapted Neutrosophic imputation methods under conditions established in the analytical study, and the simulation findings exhibited the superiority of the proposed Neutrosophic imputation over the adapted ones, and the usefulness and practical relevance of these methods are further supported by examples from Neutrosophic real data, highlighting their importance in improving the accuracy and reliability of statistical conclusion. Thus, the proposed enhanced Neutrosophic imputation methods can be used for the estimation of population mean in presence of missing data, provided the Neutrosophic data are provided in Neutrosophic. These are the references, and thank you.